Today, now we can start the talk. Today we have the pleasure of having Sabine Bögli from Durham University, who will talk to us about the discrete eigenvalues of Schrödinger operators with complex potentials. So Sabine, the floor is yours.
Thank you very much for the introduction and for the opportunity to speak here in this seminar, Spectral Geometry in the Clouds. Just to say that the geometry part is quite simple here. I'm just talking in RD. So I'm talking about Schrödinger operators, and I make my life difficult by looking at complex potentials. And I want to tell you what I know about the discrete eigenvalues, where in the complex plane they can be. And some parts of this talk is joint work with František Štampach from Prague, and some other parts are joint work with Jean-Claude Guinet from Loughborough. So as I said, the geometry is quite simple. We are in RD. We look at Schrödinger operators, so minus Laplacian plus multiplication by a complex valued potential V. And I don't want to go too much into detail with regularity assumptions. Just think of, for example, piecewise continuous functions. My standard example, or you will see a lot that I will work with potentials that are piecewise constant even. So just characteristic function. If we first set B equal to 0, so we look at the free Laplacian, H naught, then the spectrum is equal to essential spectrum, so it's just a positive half line. And now we add a potential V that goes to 0 at infinity, so it decays. Then V is H naught compact, and so the essential spectrum is the same as just for the free Laplacian. But we may now have some discrete eigenvalues. So eigenvalues of isolated eigenvalues of finite algebraic multiplicities. And here note that I do not include embedded eigenvalues in the discrete ones. If I talk about embedded eigenvalues, I will specifically mention them in addition. And otherwise, discrete eigenvalues are outside the essential spectrum. Now I'm interested in discrete eigenvalues if I have infinitely many, where they can accumulate. They can accumulate only at the essential spectrum. And in the self-adjoint case, because then the spectrum is in the real line, the discrete spectrum has to be in the negative real line. And so the only possible accumulation point is the bottom of the essential spectrum, so 0. I'm now interested in, well, the number of eigenvalues. If we have infinitely many, how fast can they accumulate to the essential spectrum? How can we measure this accumulation rate? And then also I'm interested in just if you look at individual eigenvalues, can I say something about their distance to 0 in terms of the potential V? And in particular, what happens in the non-self-adjoint case? So first I talk about accumulation rate. A good measure of how fast the eigenvalues accumulate to the essential spectrum is given, at least in the self-adjoint case, by the Lieb-Thirring inequalities that go back to Lieb and Thirring from the 1970s. So they are for self-adjoint Schrödinger operators, so this means real valued potentials. If the potential decays at infinity so fast that V is in LP for a sufficiently large p, depending on the dimension, we know that if we sum over all discrete eigenvalues and take the modulus of them to this power, then this sum is always bounded by the LP norm of the potential to the power p. Now, if we go to the self-adjoint case, okay, maybe I should say here. So you see here, the modulus of lambda is always the distance to 0, to the bottom of the distance to the central spectrum, because the eigenvalues are all, in the self-adjoint case, they're all in the negative half line. And so the modulus is just this distance to the central spectrum. In the non-self-adjoint case, now we can have complex eigenvalues that are somewhere in the complex plane, and they could accumulate at a non-zero point. But then if they accumulate at a non-zero point, and you would like to know whether this inequality still holds for the non-self-adjoint case, we run into a problem, because this distance to 0 here now will no longer be a 0 sequence if this converges to a non-zero point. And so the left-hand side will be infinite, whereas the right-hand side is still finite if we work with an LP potential. So if such an example exists, then this proves that the Liptering inequalities no longer hold in the non-self-adjoint case, and they somehow need to be adapted. And I think some of you, or many of you, have seen this result from 2017. If you take p greater than the dimension, I claim that I can construct a potential whose LP norm and L infinity norm is arbitrarily small, and there exist infinitely many eigenvalues in the lower complex half plane, and they accumulate everywhere at the central spectrum. So in particular, we have non-zero accumulation points of complex eigenvalues. And so we need to somehow modify the Liptering inequalities to accommodate also the non-self-adjoint case. Note also that if we just look at individual eigenvalues, you see that we can have arbitrarily small LP norm of the potential, but eigenvalues that are arbitrarily far away from 0. So the modulus can be arbitrarily large. This brings me to a remark about the sharpness of my assumption. In the previous theorem, you may remember I had that p is greater than the dimension. In dimension 1, this is sharp, because then p is greater than 1 if we now look at L1 potentials. So p equal to the dimension, we cannot have such an eigenvalue picture, because by a result of Abramov, Aslanian, and Davies, all discrete eigenvalues are always bounded by the L1 norm of the potential. So this assumption of p greater than 1, that is sharp in d equal to 1. In higher dimensions, this is connected to the conjecture by Labdev and Sofronov. They conjectured that if you take p greater than d over 2, as you usually do in Liptering inequalities, but less or equal to d, then again your discrete eigenvalue is always bounded by the LP norm to the power p. Now, if this conjecture were true, because the highest possible p is here d, then my assumption is sharp. but it turns out that in some cases this conjecture is not true. So let me tell you a bit about the history of this conjecture. Frank and Simon proved that such an inequality is true if you consider only potentials that are radial. And Rupert Frank also proved the conjecture for general potentials, but only if P is in this interval here, d over 2 up to d plus 1 over 2. And now if you compare this interval to the interval in the conjecture, you see that it's still open or was open for this interval of P. And I will show you in the second part of the talk, or later in this talk, that in this interval, the conjecture is false. Jean-Claude Cunet and I found a counterexample. Now, I announced this here already, because if you have a counterexample to the conjecture, then you can use this and modify here my proof of this theorem to then also get again such an eigenvalue picture, but now for P greater than what we have here, d plus 1 over 2 here. So although it turns out that the conjecture is false, one can now modify the previous theorem to then have a sharp P dependence. Okay, but now I want to come back to Liptirian inequalities before I go to the Laptev-Safronov conjecture. So we somehow want to modify the Liptirian inequality to make it hold also in the non-self-adjoint case. There are some versions that exist already since a while. Frank, Laptev, Lieb, and Zeiringer proved that if you take the sum only over all eigenvalues in the left half plane, then you still have such an inequality. Or also, if you now want to go into the right half plane, you can do this, but you always have to exclude a sector around the essential spectrum of, well, in this result here of semi-angle arccosentangent of T. And now the right-hand side here depends on T. So if you make your angle small of that sector that you want to exclude, because that's a problematic sector, if you make it small, then this constant here on the right will explode asymptotically as T to the minus P when you make T small. Then using this inequality, Demuth, Hansmann, and Catriel could follow that if you take the sum now over all discrete eigenvalues, you get a Liptirian type inequality. But well, first of all, you do not only have the modulus of lambda, which is the distance to 0, but you also now have the distance to the essential spectrum that comes in. And the distance to the essential spectrum is less or equal to the distance to 0. But if you have, in the self-adjoint case, always you have eigenvalue, the discrete eigenvalues are in the negative half plane. So the distance to 0 is the same as the distance to the essential spectrum. So if you take here again, you replace the distance by the modulus, you then see that you just get back the modulus of lambda to the power P minus D over 2, which is the left-hand side in the classical Liptirian inequality. So you recover the classical result, which is nice. But in this result here, they had to add this constant epsilon here, positive, arbitrarily small, but yeah, so the distance to the power epsilon, well, p plus epsilon over the modulus to the power d over 2 plus epsilon. And it would be nice if this would hold also for epsilon equal to 0. So they published this as an open problem to prove that such an inequality can hold, or to find a counterexample. I should say also, if I go back here on the right-hand side, this constant depends on epsilon. And if you look at their proof, this constant, the dependence on epsilon is going to infinity if you send epsilon to 0, which is not a proof that it cannot hold, but maybe a suggestion. Here is a counterexample. So now with František-Stampach, we proved, at least in one dimension so far, that such an inequality cannot hold. And our class of counterexamples, or well, we take a sequence of potentials. Our potentials are, well, the kind of easiest case that I can still compute its eigenvalues. I just take a characteristic function chi on the interval -1 to 1, and I multiply it by a complex number, I h for height, not semi-classical parameter. So this is my complex potential, and we could prove that if we take this left-hand side and divide by the right-hand side, so this is here, the LP norm to the power p, if we now send our height to infinity, then this is infinity. And actually, it was growing asymptotically as logarithm of this h. So somehow one needs to modify this here a bit, make it a bit weaker, and somehow accommodate this logarithmic term here. And this leads me to a very new result that I just finished last week, and will appear on the archive tomorrow. I now take, you see here the same as before, I multiply the left-hand side by a function that depends logarithmically on this quotient, which is 1 in the self-adjoint case, and otherwise gives you a contribution. My function f is continuous and decreasing, or non-increasing, and it shall decrease so fast that it's in L1, so this interval is finite. Then such an inequality exists. And the proof is, well, I just adapted the proof of Demuth, Hansmann, and Catriel. Maybe let me go back. So their result was take this inequality, multiply both sides by a function of t, and then integrate over t between 0 and 1. And remember that here this right-hand side was problematic at t equal to 0. So you have here t to the minus p. So you have to somehow multiply by something that makes this t dependence here still integrable near 0. That's why I multiply by t to the p times t inverse times f of minus log t. And now if you make change of variable s equal to minus log t, you obtain on the right-hand side your potential to the power p times this integral, which is finite. And on the left-hand side, you obtain this factor. Now, they just somehow didn't realize that their way of proving this was not optimal. Their result would correspond to the function f being this exponential to the minus epsilon s, because I have here a logarithmic term. If I take the exponential again, I then get s to the power epsilon. So I need this quotient to the power epsilon, which is exactly the result. If we go back here, we have the quotient to the power epsilon. And now we have this new result, which can be made better if you take a function that is going to 0 a bit, well, less fast than an exponential function. You can take, for example, 1 over s to the power 1 plus epsilon, which is an L1 function. Well, maybe not at 0, but just I'm interested in the decay at infinity. Or 1 over s times 1 over log s to the power 1 plus epsilon, or if you have in the denominator s times log s times log s to the power 1 plus epsilon, and so on. There is no best function that is still integrable, because you can always find functions that are still decaying at a slower rate. So I have this assumption that f needs to be an L1, and it turns out that this is sharp, again, at least in dimension 1. If I take a function f that is not an L1, so the integral is infinite, I can find, again, a counterexample. So if I take here the left-hand side and divide by the right-hand side, and take the supremum over all LP potentials, this is infinite. And here I take again the same class of potentials as before with František-Stampach. So we take here these characteristic functions and multiply them by a height that we then send to infinity. So then it turns out that on the right-hand side, you then get this interval, this integral, which is infinity. So this seems to be optimal, this new inequality for an L1 function here. So I'm happy with these new Lieb-Thirring type inequalities, and I will now go to the Lambda-Safronov conjecture. So recall that this was the conjecture by Lobdev and Safronov. And I told you already that Rupert Frank proved this for certain p's. In fact, he could also prove it for embedded eigenvalues. So here this is formulated for discrete eigenvalues. But if you are in this p interval, then also if you take Z to be an embedded eigenvalue, if you find a potential such that the Schrödinger operator has an embedded eigenvalue, which is an interesting problem for itself, then also the embedded eigenvalue satisfies this inequality. Now going on again in the history of the Lobdev-Safronov conjecture, Frank and Simon almost disproved the conjecture for p greater than d plus 1 over 2. Almost, because this was formulated for discrete eigenvalues, and their counterexample is with embedded eigenvalues embedded in the essential spectrum. So they found a sequence of LP potentials such that the LP norm is going to 0, but z equal to 1 is always an eigenvalue. So the left-hand side is always 1, but the right-hand side is going to 0. Now, because for these p's here, the result is true for discrete eigenvalues and for embedded eigenvalues, it somehow suggests that the inequality is true whenever it's true for embedded eigenvalues. So it kind of suggests that because we have an almost counterexample that probably the conjecture is false also for discrete eigenvalues. But they couldn't somehow adapt this example here because you have embedded eigenvalues, and somehow now you should perturb this eigenvalue of the real axis to make it isolated, to make it be in the set of discrete eigenvalues, which is very difficult to perturb embedded eigenvalues of the real axis. Instead, Rupert Frank found another new estimate. Namely, he found a weaker version where, remember that the distance to the essential spectrum is always less or equal to the modulus, so the distance to 0. He now found this estimate where you have the distance to the power p minus d plus 1 over 2 times the modulus to the power 1/2. If you add the exponents, you get again p minus d over 2. So he found a way to somehow split them to prove a new inequality. And this inequality reduces again to the original inequality if you are in the self-adjoint case. So if your eigenvalue is in the negative real half-line. Now, let's go to the counterexample for the case that was still open. We construct potentials V epsilon that depend on epsilon. Not completely explicitly, but I claim we can construct potentials such that pointwise in modulus the potential is less or equal to a constant times epsilon times the characteristic function of this set here. So we are in higher dimensions, RD, and we write every x as, well, the first component is x1, and all others are in this x dash. And we take now such a tube where the x1 component is less than 1 over epsilon. And so that's very large. And in the other component, we are only square root of it large. And now I claim that we have such a potential such that 1 plus I epsilon is an eigenvalue of this Schrödinger operator with this potential V epsilon. Obviously then, if this is true, if we send epsilon to 0, this set epsilon, which is 1 plus I epsilon, is converging from the non-real line into the real line to 1. And if we estimate the LP norm by the power p, to the power p, we can use this estimate here. So we have a constant, and then we have epsilon to the power p, and then to get the LP norm, we have to integrate this here to the power p. So the characteristic function to the power p is again the characteristic function. So we just need to find the volume of this tube. And it turns out this is epsilon to the minus d plus 1 over 2. And we have this epsilon to the power p from the height of our potential. Now you see that if our p is greater than d plus 1 over 2, then this right-hand side will converge to 0. But the modulus of our eigenvalue converges to 1. So this is then a counterexample to the Lambda-Safronov conjecture, because the modulus is not bounded by the LP norm. And then we also see that, okay, I use this inequality again, the LP norm to the power p is less or equal to this epsilon dependence here. This is actually asymptotically the same as this left-hand side of Rupert Frank's new result from the previous slide. If we go back here, we had that this combination here is bounded by the LP norm to the power p, but it's actually for this class of potentials here, this is not only less or equal to the LP norm to the power p, but it's also greater or equal to the LP norm to the power p, which proves that this combination of where you put your exponent of the distance to 0 and the distance to the essential spectrum is optimal in Rupert Frank's result. So this is the optimal way of generalizing this Lambda-Safronov inequality to p's that satisfy this inequality. Okay, so far I haven't proved much. I just said we can construct such potentials. So we want to somehow find for every epsilon potential such that 1 plus I epsilon is an eigenvalue and the potential satisfies this pointwise inequality. Here, the main ingredient is this key lemma, and this actually holds for many more perturbations of self-adjoint operators. So if you have your favorite self-adjoint operator and you want to know how you can perturb, let's say, an embedded eigenvalue of the real line, maybe you want to try and check whether you can use this method. So we take our favorite self-adjoint operator H naught and a point in its spectrum, and we take a positive epsilon. Then I claim that there exists a bounded potential such that lambda plus I epsilon is an eigenvalue of this H naught plus this potential V. And V satisfies this pointwise bound. On the right-hand side, we have a characteristic function. I haven't told you on what set, it's just we take an arbitrary characteristic function, chi. But then in this inequality, we have then in front a constant, an operator norm to the power -1. And here this chi will occur again, and our favorite self-adjoint operator H naught. So here this quotient just means, so 1 over this operator is its inverse. So we take this self-adjoint operator H naught minus our spectral point lambda, we square it. That's then a non-negative operator. And then we add a positive operator, a scalar epsilon squared. So that's certainly positive. So we can invert it. And then it's a bounded operator. And we multiply from the left and right by a characteristic function, which is a bounded operator. So we can take this operator norm and take its inverse. Okay, and I want to show you the proof of this key lemma because it's key and fun. So here is the key lemma again. I want to prove it now. So all of this here in the operator norm, I denote as k. I told you already that this here in the middle is a positive operator. If I multiply it by the characteristic function from the left and right, it's then a non-negative operator. In our case, it's also a compact operator. You can prove that in order that this combination is compact, chi needs to be H naught relative compact, which is true in our case if we take chi to be the characteristic function of a bounded set and H naught is the Laplacian in our case. So if your H naught is your favorite self-adjoint operator that is not the Laplacian, you can think whether a chi is still H naught compact. Then for a non-negative compact operator, we know that the norm of k is an eigenvalue. It's the largest eigenvalue. So we find a non-zero function phi that is our eigenfunction to this eigenvalue norm of k. And for the following, I want to take phi to be a real valued. I can do this here because our k commutes with complex conjugation. You can show that our k commutes with complex conjugation if and only if H naught commutes with complex conjugation. So if you take, in our case, the Laplacian of a function and then take its complex conjugate, this is the same as if you apply the Laplacian to the complex conjugate of your function. So they commute. And then you know that if k commutes with complex conjugation, then you can find a basis of eigenfunctions that where all the basis functions are real valued. So we can, without loss of generality, assume that our eigenfunction is real valued. I also need in the following that if I multiply my eigenfunction with chi, because I want to then apply k, so here the first thing that I apply will be a chi, the characteristic function. I want that this is phi again. You can see this if you look at the eigenvalue equation and you multiply this by chi from the left. Then on the left-hand side, you have chi times k, but you have here a chi already. And if you square a characteristic function, you just get the characteristic function again. And then you have here chi phi. And then if you multiply by the norm inverse, you see that chi phi is phi again. Okay, I use this all because now I want to write my wonderful resolvent here in a different way. So that's the middle term of our compact operator. This is actually just the imaginary part of our resolvent at the point z. So it's your resolvent minus the joint operator. H naught is self-adjoint, so you just get a set bar here in your adjoint operator. So the operator minus its adjoint over 2i, that's the imaginary part of this operator. Turns out it's exactly what we are working with here. And now I want to apply this whole operator k to my eigenfunction phi. Then, okay, so I want k phi. I know that if I just apply the characteristic function to phi, it's phi again. So I can neglect this chi here, and I apply now this resolvent, which is this combination here. So I apply this resolvent to phi, which I denote as my new function psi. And then I also apply the adjoint operator. And it turns out because k commutes with complex conjugation, because H naught commutes with complex conjugation, that here you just get the complex conjugate of this here, psi. So here you have the imaginary part of an operator, but then it turns out you just get psi minus complex conjugate of psi over 2i. So you get the imaginary part of your function. And then, so we have applied chi and we have applied the resolvent, we have to apply another chi. That's why I have here a chi and then the imaginary part of psi. And on the right-hand side, I have the norm of k times phi, but phi is this combination here, H naught minus z applied to psi. And now we're almost finished. I now want to take this norm on the other side and then write this perturbation on the left as a potential. So in order to write it as a potential applied to psi, I need to divide by psi. So my potential in the end is this left-hand side, the imaginary part of psi divided by psi, which I want to do only if psi is, well, at points where psi is non-zero. That's why I define here this nodal set, all x in the support of chi. So the nodal set within chi where psi vanishes. And then I multiply now not by chi, but slightly, well, the characteristic function of a slightly smaller set. I take the support of chi, but take away the nodal set. And now if you have your eigenvalue equation, so your self-adjoint operator minus z psi, and now plus the potential applied to psi, what is left is something on the nodal set. So characteristic function of the nodal set times the imaginary part of psi, but on the nodal set psi is 0, so certainly the imaginary part is 0 as well. So this vanishes everywhere. And you see that then you have this eigenvalue equation. So z is an eigenvalue of H naught plus v. So this is the claim, z is an eigenvalue of H naught plus v. And now let's check whether we have this pointwise bound. So we have v, now we take the modulus, so this minus doesn't matter. And then we have the modulus of imaginary part of psi over psi, but this is always bounded by 1. And all we have left is the characteristic function of this here, which we estimate from above by the characteristic function chi, because we don't know what this nodal set is in the end. and then this norm of k, which is this here, with power -1. So this is how you can perturb an embedded eigenvalue of the real axis. And in order to finish the proof of the counterexample, I don't have much time left. So we now, maybe I go back and show you what I want to prove. So far, we have constructed some potentials that satisfy certain bounds, but we don't have this nice epsilon bound here. We have an ugly norm that we need to control. Go back. So far, for every epsilon, we know that 1 plus I epsilon is an eigenvalue of H0 plus V epsilon, I should say, where V epsilon satisfies this pointwise bound. I now want to show that this here is bounded by a constant times epsilon. If I take chi to be this chi epsilon, the characteristic function of this tube, so one has to estimate this operator norm, which one can do in several ways, but I think I don't have time to say more about this. It's more or less, well, it's a bit technical. Maybe I can tell you a bit why we chose this characteristic function, or the support of the characteristic function. This has to do with this almost counterexample by the Frank and by Simon, where their potential also lived on, well, you could scale it also in this way. So x1 was living on this scale epsilon to the -1 and x prime on epsilon to the -1/2. And actually, one can show the following perturbation result, which one can then apply to this almost counterexample of Frank and Simon. One can reformulate, or as a corollary of the key lemma, one can prove that if you have an eigenvalue, an embedded eigenvalue, lambda of H0. Okay, sorry, maybe I start from the top. If you take lambda, a point in the spectrum of your favorite self-adjoint operator, and some test function psi, which in the end I take as an eigenfunction, a test function that is normalized, and I take chi to be the characteristic function of a large set, so large that it contains more or less the whole of the measure of my eigenfunction, of my test function. So the L2 norm is, well, of the whole thing it would be 1, but on chi, it's 3/4, or 1 minus chi multiplied by psi has L2 norm less or equal to 1/4. So all the measure is somehow on chi. Then if you take epsilon, well, preferably small, but larger than this error term here, which is 0 if psi is an eigenfunction to the eigenvalue lambda. If epsilon is greater or equal to this right-hand side, you can use the key lemma to prove that there exists a potential with this pointwise bound. The modulus is bounded by 4 epsilon times chi. And lambda plus I epsilon is an eigenvalue of this perturbed operator now. So in particular, if this right-hand side here vanishes, if lambda is an eigenvalue and psi is its eigenfunction, for every epsilon, you find a potential with that is pointwise bounded by 4 epsilon times the characteristic function, and lambda plus I epsilon is an eigenvalue of h naught plus this v, depending on epsilon. Now, you can use this to apply to the example by Frank and Simon, where they had an embedded eigenvalue and their eigenfunction was living on this tube that I showed you on the last slide, to then prove that this operator norm to the inverse is actually indeed a constant times epsilon. And therefore, you can perturb the eigenvalue of the real axis. I think, yeah, okay. Here are a few references. These last two papers are very new, in particular the last one with the improved Lipetiering type inequalities will appear on arXiv only tomorrow. Thank you for your attention, and I'm happy to answer any questions that you may have.
Thank you, Sabine, for the talk. Now we can take a few questions. So if you have questions, you can either ask them in chat or unmute yourself and ask them directly right now. I have one to start the ball myself. So you in this new paper appearing tomorrow, you have this improved Lipetiering inequality with these L1 function of the logarithm of the distance appearing as an extra term. Presumably, when you say that the Frank-Simon bound or Frank-Simon range is sharp, there is still some space between p greater than d plus 1 over 2 and p equals d plus 1 over 2.
Sorry, I forgot to say that. Yes, let me go back. So here I have p greater or equal to d over 2 plus 1. But this is because I need to apply this result, which also is only for d over 2 plus 1. So also then in my, well, I can show only in one dimension that I have this sharpness. Yeah. And here I take p greater or equal to 1, whereas, well, for d equal to 1, you have here 3/4. So also in between there, it's not clear whether, well, okay. The sharpness result shows you you cannot use a function that is not in L1, but I'm not sure that this theorem still holds for smaller p's. And also in higher dimensions, I don't know what happens between, whether this is true between d over 2 and d over 2 plus 1. And also, I do not yet have a sharpness result.
I mean, yeah, my question was more related to the Laptev-Safronov conjecture.
Ah, sorry.
Instead, so in the Laptev-Safronov conjecture, so Frank proved, and if you combine the result of Frank and Simon, we have that this is true for p up to d plus 1 over 2, and you prove that it's not true if you take p greater than d plus 1 over 2, but presumably there is some logarithmic bound or sharp term.
No, the best result is this one. This one is now the best result.
So this is the best result, but and is this completely optimal, or you could find some sort of in between?
If you want to have a result that reduces to this here in the self-adjoint case, and you just, I mean, you can take various combinations of here the distance to 0 and the distance to the essential spectrum, but because you have here that this is going to 0 in exactly the same order as the right-hand side, if you would change your exponents, then your left-hand side divided by right-hand side would go to infinity. If you take a larger exponent here, and then you need to take a smaller exponent here.
All right. Yeah, and I guess it's the same thing if you add the logarithmic type term to this inequality as well. You'll see the same thing. All right. Does anybody have any other question for Sabine?
Could I ask a question, please?
Yes, of course, Marco.
So Sabine, I was trying to pay attention during your proof of the key lemma, and at some point it must be important that lambda lies in the spectrum of H0, right? Because otherwise I just don't see how the result could be true. But I didn't see where in the proof you used it. That
I didn't use it. Well, okay. No, I didn't use it. I use it then to prove that this here is bounded by epsilon.
Right. So
yeah, generally you just have, okay, if I go to the general, there's this key lemma. Okay, here you wouldn't need it.
Okay.
I agree. But then you will not, this will be, this to the inverse will be very large. Or you cannot make it small, probably.
Right, yes, I see. Okay, I've just spotted there's a -1 there, which I can just see on my tiny little screen. Yes. Okay, now I understand. Yeah, now I understand.
Minus lambda, yes.
Yeah. Because you could, even if you sent, if you sent lambda to infinity, this thing would blow up, right?
Yes.
Thanks.
All right. Thanks, Marco, for the clarifications. Is there any other questions now? All right. Well, if not, let's thank Sabine again, and we'll reconvene next week at the same time for a talk by Ben Sharp.